Hello everyone, my name is Rafid Bendimerad, and today I'm going to talk about the work that I've done over the past 3 years in my PhD program that I titled Multiscale Modeling of Electrosphere Thrusters Plume using Molecular Dynamics and M-body Simulations. The topic of this presentation is about propulsion. In general, when we think about propulsion, we think of a big rocket leaving Earth, ejecting a lot of exhaust gas. However, in this presentation, we are going to focus on in-space propulsion, in which we are already in space and we don't need to overcome the strong Earth gravity pull and the air drag. There are two main categories of propulsion systems that we can use in space. The first one is chemical propulsion, in which we mix a fuel with an oxidizer or a catalyst to produce a combustion or a chemical reaction. And then the exhaust gas will produce thrust by conservation of momentum. The second category is electric propulsion, in which we use a noble gas that we ionize, or we can also use molecular ions, and then we apply a strong electric field to extract the ions, and then we produce thrust. In this presentation, we are going to focus on electric propulsion. And then we can ask why electric propulsion. There are many considerations based on which we prefer electric propulsion over chemical propulsion. The first consideration is specific impulse. The specific impulse is a metric that is used to quantify how well a spacecraft uses its fuel to produce thrust. It is given by this formula here, which is the ratio of the thrust to the propellant mass flow rate times the gravity at Earth's surface. For example, if we have two identical spacecraft with the same thrust but a different specific impulse, if this blue spacecraft has a higher specific impulse than the pink one, then the blue one will be able to work or operate over a longer period of time because it consumes less propellant mass flow rate. Similarly, for a smaller amount of fuel, it will be able to operate over the same amount of time. And this figure here gives the specific impulse as a function of the thrust. And we can observe that all electric propulsion systems happen to be in the upper part of this figure. So electric propulsion is characterized by a high specific impulse. And in our work, we are specifically interested in electrosphere thrusters. We can also ask why electrosphere thrusters. And the reason is that there are many limitations that we find in other types of propulsion systems that the electrosphere thrusters can easily overcome. For example, let's take the Hall thrusters that are one of the main popular electric propulsion systems. Hall thrusters are used, for example, in SpaceX for Starlink, and we can see that they can produce about 2500 seconds of specific impulse. However, we can also see that the total efficiency is about 50%. And the reason is that Hall thrusters require an ionization process that consumes about 50% of the power. So if we start with a noble gas, that is argon, for example, of xenon, we have to bombard this noble gas to ionize it and then use it for propulsion. And this step here consumes a lot of power. The second limitation is complexity. So for example, Hall thrusters require a magnetic field plus an electric field. The third limitation is scalability. So in the past years, there is a tendency in the aerospace engineering to launch smaller satellites. And Hall thrusters are challenging to scale down. And the fourth limitation is precision. Hall thrusters do not provide fine thrust control. And this last point is very important because when we are in space and we have a spacecraft, the spacecraft is subject to external perturbations. So if we have these perturbations inward, we have to apply an attitude dynamics and control forces to cancel the perturbations to obtain this green stable system. For example, if we take this mission, the LISA mission that is planned for 2037, in which we have three spacecraft away from each other by a distance of 2.5 million kilometers. Each one of them has to send and receive a signal, a laser signal. And the precision and stability requirements are very high for this mission. So we want a thruster with a high specific impulse, a high thrust precision, and scalable to smaller sizes. And for all these reasons, the European Space Agency has chosen the electrospray thrusters to be used for the LISA mission. So for the next of this presentation, I'm going to focus on the electrospray thrusters. This is this this is a diagram that shows an electrospray thruster. Electrospray thrusters use ionic liquids as propellant, and ionic liquids are just a molten salt, very similar to the table salt that we use in everyday life. However, the melting temperature of the table salt is about 800 degrees, whereas the ionic liquids are liquids at room temperature. They are also liquids at very low pressure. And they are composed of one big cation, the positive part, and one small anion, the negative part. And the ionic liquid that we use for our application is EMIBr4 that is given with this chemical formula and this chemical structure. So since the ionic liquid is liquid at room temperature and very low pressure, so we don't need any pressurization or heating. And there is also no moving part in this system, and there is no ionization process needed, and there is no magnetic field and no combustion. So this is a very simple system. And then we use a porous needle, so the fluid can go through the needle due to the surface tension. And then when the fluid reaches this tip of the emitter, we can apply a strong electric field to extract the ions. And we can operate in the positive mode to extract EMI plus or in the negative mode to extract Br4 minus. And the ions are extracted at a very high speed, about 50 kilometers per second. And this creates thrust. And there's also scalability. So this figure here shows a spacecraft that has many arrays on its back, and each array contains about 500 emitters, and each emitter is one electrospray thruster that we have shown in the previous slide. So in one single spacecraft, we can use thousands of electrospray thrusters. And then I'm going to talk about the main limitation of electrospray thrusters, which is polydispersivity. So what this figure shows is the optimal operating conditions in which we operate in pure ionic regime. We only have ions. However, in actual operating conditions, we have monomers, dimers, trimers, etc. A monomer is just a molecular ion. A dimer is a neutral attached to an ion. A trimer is two neutrals attached to an ion. And in addition to these three different molecules that we get within the plume, we also have fragmentation. So these complex molecules also fragment to give neutrals and ions. So we have different species here with different mass to charge ratio. And the specific impulse, the ISP, is proportional to the square root of the charge to the mass, whereas the thrust is proportional to the square root of the mass to the charge. So heavy molecules contribute more to the thrust, and light molecules contribute more to the specific impulse. But this difference in the charge to mass ratio within the plume creates some imbalance in the plume that we are trying to study and understand. And we try to understand the evolution of the plume. And we do this using multiscale modeling. So the single emitter is in the range of hundreds of microns. And we also try to understand the interatomic interactions within the atoms of the molecules in the angstrom scale. We also model the meniscus in about 50 nanometer scale. And later on, we want to expand these simulations to include interacting beamlets and multi-emitter arrays and spacecraft plume interactions. And in my PhD, I focus on these two different scales, the angstrom scale, in which I use molecular dynamic simulations to simulate the interactions between the atoms of the molecules within the plume. And I use N-body simulations to simulate the full plume in hundreds of microns. So for the rest of this presentation, I'm going to talk about the full plume simulation in the micrometer to the millimeter scale. Then I'm going to talk about molecule-molecule and molecule surface interactions in the angstrom to nanometer scale. And then I will conclude. So for the full plume simulations, we need initial conditions of emission. We need the definition of the external electric field distribution. We need a fragmentation model, and then we need an algorithm to propagate the particles. The initial conditions of emission were provided by Sidon Chachimo in his PhD thesis, where he used an electrohydrodynamics model to model the meniscus of the liquid. And this figure here gives the probability density of emission as a function of the radius, which is the radial distance from the axis. And we see that all emission happens within the range of 20 nanometers from the axis. And there's no emission starting from this region here. And then in the middle, we have the initial velocity. We have VR, that is the radial velocity, and VZ, that is the axial velocity, as a function of the radius. And then we have the electric field distribution, and we can see that the magnitude of the electric field is very high near the emitter, and then it vanishes away when we go far from the emitter. And we also have the plume composition that is composed of 40% monomers, 40% dimers, and 20% trimers. And then we have a fragmentation model provided by Schroeder et al. And this paper gives the probability of fragmentation at each time step dt as an exponential decay that is given by this equation here, where dt is the time step and tau is the mean lifetime. And the mean lifetime is given as a polynomial of the magnitude of the electric field. And the coefficients of this polynomial depend on the type of species. So we have here the coefficients for primary dimers, trimers, and secondary dimers. And then when we get the mean lifetime, we can compute the probability of fragmentation for each species. And then we need an algorithm to propagate the particles. And each particle in the system is subject to two forces. First, there is the electrostatic force that is due to the external electric field. And then there is the Coulomb force that is due to the interaction between the particles. So we need an algorithm to compute the acceleration of the n particles. And then we need an algorithm to update the position of the n particles. So to compute the acceleration, we just use a direct force algorithm where we sum up all these different forces plus the electrostatic force, and then we compute the acceleration. And then to propagate the particles to the next time step, we use the leapfrog algorithm, where we update the velocity by half step, and then we update the position by a full step, and then we compute the acceleration, and then we update the second half step of the velocity. And this algorithm is a symplectic integrator, which means that it conserves the phase space of the Hamiltonian. And over long time steps, it conserves the overall energy of the system. And then we divide the domain into three regions. So in region one, there is a very high density. So the interparticle forces are of the same order as the electrostatic forces. So we compute the two forces at each time step. And then in region two, between 5 and 250 micrometers, the interparticle forces represent about 1% of the electrostatic forces. So we only calculate the interparticle forces at each 10 time steps. And then beyond region 2, in region 3, beyond 250 microns, both forces are very weak, so the acceleration is considered to be zero, and we propagate the particles at a constant velocity. And this is an animation of the simulation. In the left, we have the 3D simulation, the 3D view, and on the right, we have the 2D view. So the red particles represent monomers, the green ones represent dimers, and the blue one represent trimers. And then we can see fragmentation happening near the emitter to get neutrals as well. And these neutrals have a very low speed. And then we get this result here after emitting 300,000 particles with a time step of 5 femtoseconds. And the criterion of convergence that we used is the number of neutrals in region 1 and 2. And we see that there is sort of convergence when we reach about 70 or 80,000 time steps. And then we try to uh, increase the performance of the code by using a just-in-time compiler called Numba that we use with NumPy. And the role of the just-in-time compiler is to translate the high-level Python into a low-level machine code that is much faster. And as we can see, we gain about 2 order of magnitudes in terms of the computation time of the acceleration. And there is a second way that we can use to uh, increase the performance of the algorithm, which is the far-field approximation. So if we have a particle here and we have a cluster of particles far away, we can approximate this cluster of particles by one big particle located at the center of mass. However, this approximation is not valid if the cluster is very close to the particle. So in the direct force algorithm, we compute particle-particle interactions. So the complexity is n squared. We do about n squared computations for n given particles. And then there is this algorithm called Barnes-Hart algorithm, in which we approximate the source and we compute cluster-to-particle interactions. And the complexity here is n log n being the number of particles. And then there is the fast multiple method, the FMM, where we approximate both the source and the target, and we do cluster-to-cluster interactions, and the complexity here is n. And I tried to implement this FMM algorithm using the ExaFMM library on Python by Barber Group. And this library allows us to prescribe the value of P, which is the order of expansion of the FMM code. So when P is higher, the accuracy is higher as well, but we do also more computations. And ncrit, which is the maximum number of bodies per leaf. And the implementation of the FMM with the ExaFMM library is very easy. We only have to define the sources and the targets and the order of expansion P and the n-critical 100 here. And then this gives us the potential and the gradient of the potential that we can use to compute the electric field and the electric force. However, this didn't give any significant improvement. And this can be explained with this graph here. So Hempel et al. Showed that here showed in this graph the computation time versus the number of particles for the direct force in green, Barnes-Hart in blue, and EFMM in red. And they showed that the FMM and the Barnes-Hart start being faster than the direct force starting from 4,000 particles. However, in our case, we are in region 1, we have about hundreds of particles. In region 2, we have up to 2,000 particles. And in region 3, we have the rest of particles. And most computations happen in this region one. So that is why we don't see any improvement. So in this region, the direct force is faster than the FMM. And here again, we have the simulation. And this on the right, it's a zoomed in image of the simulation near the tip. And we can observe two main things here. We see that the neutral collides with the grid, and we see also collisions between the monomer and the neutral. Even though in the n-body simulations, we don't implement the collisions, as we see here that the neutral penetrates the grid. But this informs us that these collisions happen, and we can use this information to inform our molecular dynamics simulations. So for the next of the presentation, I'm going to talk about molecular dynamic simulations that we use to simulate intermolecule collisions and molecule surface collisions. So first, let's talk about molecule-molecule interactions at the angstrom to nanometer scale. So the approach here is molecular dynamic simulations. The software that I used is LAMPS, which is a dedicated software for MD simulations. And there is a critical step in MD simulations, which is the choice of the force field. And here we use a reactive force field, the ReactFF. The main advantage of this reactive force field is that it is able to capture the breaking of covalent bonds and therefore simulate chemical reactions. However, it is ill-defined for charge systems, so we are unable to track the distribution of the charge in this system. And since the byproducts of the collisions uh, depend on how the projectile lands on the target, so we do a statistical analysis by rotating the two molecules. We define these parameters, phi y and phi z, and theta y and theta z. And we also define this parameter, the impact parameter, that is the distance between the two centers of mass of the projectile and the target. And we vary these particles to do a statistical analysis. And we also vary the impact energy between 10 and 1000 EV. And the total number of simulations that we get is about 18,000 simulations. And here is what we observe in the simulations. So at small impact energies, we see recombination. So the two molecules stick together. And also we observe momentum exchange. So the two molecules do not stick together, but there is an exchange of momentum. And we also see charge exchange. So the projectile takes the negative uh, ion of the target. So this EMI plus takes the BFR minus of the other EMI. And then between 10 and 30 eV, we see ionic fragmentation. So the ionic bond between EMI plus and BFR minus fragment, and we get these two molecules. And then at impact energies higher than 30 eV, we see covalent fragmentation. So the covalent bonds within the molecule break, and we get very small fragments. And we represent the results in the form of mass spectra. A mass spectrum has the mass in the x-axis and the probability of occurrence or the abundance in the y-axis. And since we know the mass of the atoms, we can infer the type of the molecule from its mass. And we observe that at small impact energies, we still see the initial molecules, so the fragmentation rate is very small. And then at higher impact energies, there is more fragmentation, so we see more light molecules, mainly CXHY and CXHY and Z. And then at higher impact energies, it is mainly dominated by the atom of hydrogen. And we also investigate the influence of the impact parameter B, that is the distance between the distance between the centers of mass of the two molecules. And we also define this parameter alpha, that is the ratio of the breakup products, that is the number of byproducts divided by the number of initial molecules that is 2 initially. And you observe an increase in the number of byproducts with an increase in impact energy, which means that stronger impacts lead to a higher number of fragments. And then we see a decrease with increasing B. So B equals 0 is this blue one, and B equals 6 is the pink one. And we see a decrease up to 6 angstroms. So for B equals to 6 angstroms, alpha is 1, which means there is no fragmentation. And this means that all collisions and fragmentations happen within the range of 6 angstroms. And we're also interested in the impact of these collisions on the performance. And this is the formula of the thrust. And as we can see, only axial uh, the axial velocity Vz contributes to the thrust. And the specific impulse is also dependent on the thrust. So the performance of the spacecraft depend on the axial velocity, on the axial component of the velocity. So all these off-axis deflection angles are detrimental to the overall performance of the thruster. And this figure here on the left gives the deflection angle as a function of the impact parameter, of the impact energy, sorry. And next, we are also interested in the loss of kinetic energy and the loss of axial momentum. So if you start with this system here, the kinetic energy of this monomer moving towards the neutral, this kinetic energy is higher than the sum of the kinetic energies of all these fragments. Similarly, the axial momentum of this monomer is higher than the axial momentum of all these fragments. And the loss of the kinetic energy and the axial momentum are given here in this figure in red and blue. And particularly this region, we observe a high loss of axial momentum. And this is because this region is dominated by ionic fragmentation, in which the negative monomer backstreams towards the emitter and does not contribute to the total total axial momentum. Next, I'm going to talk about molecule grid interactions. And similarly, I use molecular dynamic simulations. I use a software called LAMPS, and here I use two force fields, the reactive force field to model the interactions between the atoms of the molecule, and the Lennard-Jones potential to model the interactions between the molecule and the wall. The Lennard-Jones potential has a repulsive term and an attractive term, and these coefficients, epsilon and sigma, are given in the literature, and the potential depends on the distance of the atom I from the wall. Here again, we can capture the breaking of the covalent bond, but the disadvantage is that we have to work in an impact surface agnostic framework. So instead of having a real wall, we are using a potential wall. And here again, we do a statistical analysis by rotating the molecule about the y and z axes. And we do two sets of simulations, one for EMI wall collisions and one for EMI BF4 wall collisions. And this is an example of the simulation. We start with one big molecule that is EMI BF4, and then we end up with 9 different byproducts after the collision. And also here again, we represent the results with mass spectra. And we see that we have heavy molecules at small impact energies. And then we start seeing CXHY, CXHY, and Z, and also fluorine here at higher impact energies. And then at much higher impact energies, this is dominated by the atom of hydrogen. And then we tried to do an experimental validation of our model, and this was done uh, by Saba Sheikh, an MIT student, in the Space Propulsion Lab. And the approach was to use an array of 480 electrospray thrusters uh, to emit an ion beam into a stainless steel plate inside a vacuum chamber. And we used two instruments. One is the retarding potential analyzer, the RPA. This one measures the energy distribution of the ions before collision. And we used the residual gas analyzer, the RGA, that collects and measures the rebounding molecules after collision. So the this is the thruster. The ions are emitted from here, and then here there's the collision, and then the RGA collects these byproducts and measures them. So we use MD simulations to get the mass spectra of the byproducts of the collisions at different impact energies. And then we use the RPI measurements to get the energy distribution. So these two are for the neutrals, and then we multiply each mass spectrum by its corresponding uh, probability, and then we get an average spectrum of EMI-BF4 wall collisions. And we repeat the same procedure for EMI wall collisions by multiplying the mass spectra by their corresponding probability distribution to get an average spectrum of EMI wall collisions. And then we multiply each mass spectrum by the mass flow rate of neutrons and ions, respectively, and we sum them to get one single averaged mass spectrum that we can compare to experiments. And this figure here shows a comparison between the predicted mass spectrum in blue and the measured mass spectrum in red. And we see some qualitative agreement between the two. However, we also see some discrepancy. So mainly there's this discrepancy here. So they observe in the experiment the molecules of OH and H2O. And this is because the background gas in the vacuum chamber, so there is water in the vacuum chamber. And even though they tried to remove the background gas measurement, there's still some fragments of water in the vacuum chamber. And then there's this discrepancy here. That is, so we predict more atoms of hydrogen, but they observe more H2. And we predict more fluorine atom, F, and they observe more HF. And there are some reasons that can explain this discrepancy. So first is the recombination that can take place between the collision area and the RGA, that is about 20 centimeters. So two atoms of hydrogen can recombine to give H2, and an atom of hydrogen can recombine with an atom of F to give HF. There is also surface recombination. So for example, one atom of H can stick to the surface, and then a second atom of H can come and collide with the surface, and then these two atoms will recombine in the surface. The second explanation could be that the RGA does not have a sufficient resolution to distinguish between species within mass within plus 1 or minus 1 AMU. And finally, the third one is that the RGA has to ionize the molecules first to be able to measure them. And the ionization depends on the collision cross-section of each molecule. And therefore, the RGA has a different sensitivity to every species. So this figure here shows the ionization cross-section of H and H2. The RGA operates in this region here. And we see that the ionization cross-section of H2 is higher than the one of H. So the RGA is more sensitive to H2 than H, and that is why it measures more H2 than H. And here's the conclusion. So this presentation was divided into three parts. In the first part, I talked about the full plume simulation, in which we used an electrohydrodynamic model plus a fragmentation model plus a direct force algorithm to simulate the emission of 300,000 particles composed of monomers, dimers, and trimers. And then we identified molecule-molecule and molecule-grid collisions. Then in the second part, I talked about molecule-molecule collision simulations, in which we used a reactive force field to simulate monomer neutral collisions, and we identified five types of interactions: recombination, charge exchange, momentum exchange, ionic fragmentation, and covalent fragmentation. I also showed the species composition per impact energy between 10 and 1000 eV, and we saw that stronger collisions give lighter molecules. And we have also seen that all collisions happen within the range of 6 angstroms. And uh, we have talked about the losses of the kinetic energy and the axial momentum of particles due to collisions. And in the third part, I talked about molecule surface collision simulations, uh, in which we used a reactive force field and a Lennard-Jones potential to simulate monomer grid and the neutral grid collisions. And we have given the species composition per impact energy between 10 and 1000 eV. And finally, we did an experimental validation of the predicted mass spectrum that showed a good qualitative agreement. And this figure here shows the state of the art in 2021 when I started this project and the current state of the art in 2023. So initially we knew that we had different species within the plume: monomers, dimers, trimers, and neutrals. And now we know that in addition to these different complex molecules, we also have much lighter and smaller fragments. And this work has led to 2 journal papers and 3 conference papers that have already been presented, and 2 conference papers that will be presented in 2024. And for the future work, so we want to include collisions in the full plume simulations. So the full plume simulations plus the collisions will inform the MD simulations about the type, the rate, and the energy of collisions. And then we want to simulate the collisions by including also dimers and trimers in the MD simulations, because currently we only have monomers and neutrals. And then the MD simulations will inform the full plume simulations about the collision byproducts. And then we can use this closed loop to integrate the loss per collision over all the collisions to get the total loss due to collisions. And one challenge in including the collisions in the plume simulations is that we have very fast particles. So if we check the collisions at time t1, there is no collision. And then if you check the collisions at time t2, there is also no collisions. So here the collisions happen in the intermediate steps. So we have to take this into consideration to implement our collision detection algorithm. And finally, for IEPC, which is the International Electric Propulsion Conference in 2024, I have proposed this following project. So to get steady ion emission, uh, there are 2 main criteria that we need. So first is about the bulk properties of the ionic liquid, that are the density, the surface tension, the viscosity, the electric conductivity, etc. And second, the molecular properties, which are the molecular structure and the charge distribution, etc. And the challenge to find the appropriate ionic liquids that satisfy our conditions is that there is a very big diversity of ionic liquids. There are millions of ionic liquids that we can use. However, less than 1% has been explored experimentally. And the goal is to exploit the sparse experimental data that are available to extrapolate properties of other ionic liquids. And then from this step, we can propose new potential candidates as propellant for electrospray thrusters. And we want to use machine learning for that. So first, I'm going to talk about the data description. So currently we have data of density, viscosity, and surface tension for about 4,000 ionic liquids. And these data are presented with the simplified molecular input line entry system called SMILES. And the SMILES describes the structure of the chemical species using a string of character. It includes atoms, bonds, rings, aromaticity, etc. For example, for a given molecule, we have its corresponding SMILES representation. For example, the equal sign represent a double bond. This number one represent a ring, and the parentheses represent branching, etc. So we can represent all the details of the molecular structure of a given molecule using a string of characters. And the goal is to use this string of characters as an input for our machine learning model. So the input would be the SMILES representation of the ionic liquids plus the cation molecular weight and the anion molecular weight. And then we can feed this into a neural network. And then the neural network can predict some physical properties of these ionic liquids, such as the density, the viscosity, and the surface tension. And then I'm also planning to do a classification to classify based on structural features, the ionic liquids that are suitable or not suitable for electric propulsion. And then we can also do a feature importance based on the structural features. And finally, I want to thank our sponsors that are NASA, the AFRL, and our collaborators in the MIT, the Space Propulsion Lab. And I also want to thank my advisor, Professor Elaine Petro, and all the Astrolab members. And thank you for listening.